There are several models related to exponential and logarithmic functions. A logistics growth starts out like an exponential growth and then tapers off. It is commonly used to model the spread of diseases and was used by Sam Walton of Walmart to determine when to take items off the shelf to make room for the next hot-selling merchandise. Exponential decay is used in carbon dating and depression. Exponential growth is used to model the growth of money and population growth. Gaussian models correspond with bell curves and are often used in academia. And the natural and common logarithmic models are used when calculating the intensity of earthquakes, sound, and acidity. At the time of this writing, the current Ebola outbreak data is matching an exponential growth model. What healthcare workers and statisticians are hoping for is that the data will start to trend toward a logistics model. In the Ebola 2014 webpage and video, 2 models for the epidemic were developed. Use them to predict the number of Ebola cases on the last day of September. We'll start with our first equation. To predict the number of cases, y, we set that equal to 88.919 e to the 0.0218 times the 190th day since the epidemic was first reported. So putting this into the graphing calculator, if you were last in a graph, click on second quit to make that go away. And we will put in 88.919 times second of the natural log, e to the, and we need to take 0.0218 times 190 days. Close our parentheses and press enter. So this model is predicting 5,595 cases, actually 5,596 cases on September 30th. Using the second equation, y equals 88.919 times 1.022 to the 190th day. We'll plug that into the calculator. Raising that to the 190th power. Graphing calculator is smart enough to know what order of operations, which will take this number to the 190th power and then multiply it by the value that we're looking at. And this model predicts 5,555 cases. Since the last video was recorded, there was an update that there were an estimated 6,262 cases on September 21st. So we can see that our models are not doing as well at predicting the number of cases as we potentially would like. The CDC estimates that there will be approximately 8,000 cases, or as many as 21,000 cases, if corrections for underreporting are made. It estimates that for every Ebola case currently, there are 1.5 times as many of unreported cases. So that can help change this value. And of course, we have not taken that into consideration or compensated for that in our original equations. So let's use the second model to predict when the number of cases would reach 50,000. So 50,000 should equal 88.919 times 1.022 to the x power. solving this, we will divide both sides by 88.919. And then that will be the 1.022 to the x power. And once we have evaluated that, how do we get rid of our base if it's being raised to the exponent? We would take the log of this number. So we'll pull the calculator up, and we have 50,000 divided by 88.919. We won't clear that, we'll just leave it in the calculator. And our next step is to take the log base 1.022 of 1.022 to the x power. Do the same to both sides. And that will give us an x. But if we want the log base 1.022 of 562 and 31/100ths, that means that we need to use our change of base to either take the common log of 562 and 31/100ths over the common log of 1.022, or we could have used the natural log of both. So we will take the log of our previous answer, second of the negative sign, and we will divide that by the log of 1.022. And by not clearing out our calculator, or by using the answer that was previously given, we will not have any rounding errors here. And our answer is 291 days. Here's another example. After 2 days, a researcher observed 100 fruit flies in an environment. After 4 days, there were 200 fruit flies. If the conditions remain the same and the population follows an exponential growth model, how many fruit flies will there be after 6 days? So our exponential growth model looks like this. Y equals some number times e to some number times x. So after 2 days, there were 100 fruit flies. That means there were 100, where y is the number of flies. And we don't know what our a value is, but we know that it was 2 days, so we have a 2b here. Likewise, after 4 days, we had 200 fruit flies. So 200 equals that same coefficient times e to the 4b. So I'm going to do a substitution here. I'll solve for a. A will be 100 over e to the 2b. And let's plug that in here. 200 equals that a times e to the 4b. So 200 equals 100. If I have e to the 4b over e to the 2b, bases are the same, I can subtract the powers. I will have e to the 2b. Dividing by 100. So 2 equals e to the 2b. I'm going to take the natural log of both sides. So 2b will be equal to the natural log of 2. And so if I divide by 2, b becomes 0.347. And if b is about 0.347, then 100 over e to the 2 times 0.347 will be equal to a. So we'll take 100 divided by e to the 0.693, or 2 times our previous answer. And we get 50. So a is 50. And b is about 0.347. Substituting those in, we're able to figure out now how many fruit flies there will be after 6 days. We don't know what y is, but we know that we have 50 times e to the 0.347 times 6. And on day 6, we should have about 479 fruit flies.